Coming to the final part of the chapter, we'll be discussing molecular mass and mole concept. What is molecular mass? The molecular mass for a substance is the sum of atomic masses of all the atoms in a molecule of the substance. So we know that atoms, they combine together to form molecules. So when we have to calculate the molecular mass, we will simply be adding all the mass of the atoms. So we'll be adding all the mass of the atoms. Okay, we will be combining them, and the resultant value that we'll be getting, that will be the molecular mass. So it is therefore the relative mass of a molecule expressed in atomic mass units. Illustrate this. We'll illustrate this with an example. Let's calculate the relative molecular mass of water. So we know that 2 atoms of hydrogen and 1 atom of oxygen come together to form 1 molecule of water. So atomic mass of hydrogen is 1 U and oxygen, it is 16 U. But since we have to calculate the molecular mass, we will be focusing our attention on the number of atoms that are present here, right? Since there are 2 atoms of hydrogen, okay, so we will be multiplying the atomic mass of hydrogen, that is 1 into 2 with 2, and since there is only 1 atom of oxygen, so we'll be only multiplying 16, that is the U of oxygen, with only 1. Okay, so 2 atoms of hydrogen, all right, and 1 atom of oxygen. So the number of atoms is clear, and we are multiplying the respective amount of respective atomic mass unit with the number of atoms that are there. So 2 into 1, 1 into 16, and that is 18 U. Similarly, in the case of hydrogen nitrate, there is 1 hydrogen, okay, there is 1 atom of hydrogen, there is 1 atom of nitrogen, and there is 3 atoms of oxygen. Okay, in HNO3, the chemical formula that we have here, we see that H, okay, we are only having 1 atom of hydrogen, we are having only 1 atom of nitrogen, but for oxygen, we are having 3 atoms. So when adding, we will take just 1, that is the unit of hydrogen, then we will take 14, that is the U of nitrogen, but we will be multiplying 16 into 3 because 16 is the atomic mass unit of oxygen, and we will be multiplying it by 3. Why? Because there are 3 atoms of oxygen. So we'll be getting 48, and then we'll be adding all these together to get 63 U. Let's have a look at the formula unit mass. The formula unit mass of a substance is the sum of the atomic masses of all atoms in a formula unit of a compound. Formula unit mass is calculated in the same manner as we calculate the molecular mass, that is by adding up the atomic mass units. Alright. The only difference is that we use the word formula unit for those substances whose constituent particles are ions. So for those molecular compounds whose constituent particles are ions, instead of using the molecular mass, we'll be just using the formula unit mass. Conceptually, it is the same thing, but we just have given different terms. For example, sodium chloride, since it is the combination of the sodium cation and the chloride anion, so its formula unit mass can be calculated as 1 into 23 and 1 into 35.5. Since there is only 1 atom of oxygen, since there is only 1 atom of sodium and there is only 1 atom of chlorine. So as a result, we will be getting 58.5 U. Illustration 2. Calculate the formula unit mass of calcium chloride. In calcium chloride, like we can see from this formula, there is only 1 atom of calcium. Okay, for 1 atom of calcium, we have 2 atoms of chloride. Okay, so since we are having 2 atoms of chloride, we will be multiplying the atomic mass unit of chlorine, that is 35.5 into 2, and the atomic mass unit of calcium would be just 40, since there is only 1 atom of calcium. So 40 plus 2 into 35.5, that is 40 plus 71, that is 111 U. Let's have a look at some example questions. Calculate the molecular masses of hydrogen, oxygen, chlorine, and rest of the elements here. So let's do this in sequence. First of all, we have hydrogen. Okay, we know that the atomic mass unit of hydrogen is 1, and since we have to calculate the molecular masses, and since there are 2 atoms of hydrogen, so we will be multiplying 1 into 2. Why 2? Because we have to calculate the molecular mass. And how is molecule formed? Molecule is formed with a combination of atoms. So to calculate the molecular mass, we will have to calculate the mass. We will have to calculate the mass of the atoms together present in that molecule, and we have to combine them. We have to add them. So 1 into 2, that is 2U would be the molecular mass of H2. For O2, okay, similarly, we will be having 16, since 16 is the atomic mass unit of oxygen, into 2, since we are having 2 atoms of oxygen. So that will be 32U. Moving on, we have chlorine. So for chlorine, the atomic mass unit is 35.5. We will be multiplying it by 2 and we will be getting 71U. Then for carbon dioxide. For carbon dioxide, we have 1 atom of carbon. The atomic mass of 1 atom of carbon is 12. And since there are 2 atoms of oxygen over here, so we will be multiplying 2 into 60. That is, we will be adding 12 plus 32. So as a result, we will be getting 4 and 3 plus 1, 4. That is 44U for carbon dioxide. Next, we have methane, that is CH4. So we are having 12 as the carbon atomic mass unit of carbon. For hydrogen, since there are 4 atoms of hydrogen and we have to calculate the molecular mass, so we will be multiplying 4 into the atomic mass unit of hydrogen, that is 1. So we will be basically adding up 12 and 4, that is your 16U. Okay, it's simple, right? You just have to keep on adding the number of we have to keep a tab on the number of atoms that are there, and you have to multiply that specific number of atoms with that specific number of atomic mass unit of that particular atom. So for example, C2H6, for that we have C2H6, we have 2 atoms of 2 atoms of carbon. So that is 2 plus 12. Since 12 is the atomic mass unit of carbon, then we will add it with 6 into 1, because 1 is the atomic mass unit of your hydrogen and 6 is the number of atoms that is present in this particular molecule. So you will be getting 24 plus 6, that is 30U. Now I have solved almost all of these for you. There are only 2 left. Okay, so let's be this as your homework. All right. So for NH3, I'll be just giving you some hints. Okay, we know that nitrogen has 14 U as its atomic mass unit. Hydrogen has 1, and since there is only since there is 3 atoms of hydrogen present over here, so we will be multiplying 3 into 1. Then you'll add this up, okay, and that will be the resultant amount. The resultant value would be the molecular mass unit of NH3. For CH3OH, there is only 1 atom of carbon, so we'll be only taking 2. There is only 1 atom of hydrogen, so we're only taking, sorry, there is not 1, there is 3 atoms plus 1, 4. There is 4 atoms of hydrogen all in all. Okay, now don't hesitate to combine the value of this hydrogen and this hydrogen. Hydrogen is the same, all right. They are just combined. These elements, these atoms are basically just combined with each other in a very different format. Okay, so the basic thing is to remember the number of atoms over here. So we know that there is only 1 atom of carbon, so we have taken 12. We know that over here, just have a look, there are 4 atoms of hydrogen. Okay, there is H3 over here and there is H over here with the hydroxide. Okay, so without any hesitation, we'll add this 4 into 1, and since there is only 1 atom of oxygen, so that is 16. Okay, so we will basically just add 12, 4 and 16, and whatever the result would be, that will be the molecular mass of CH3OH. Simple, right? Question 2. Calculate the formula unit masses of zinc oxide, sodium oxide, potassium carbonate, and the given atomic masses of zinc, sodium. They are all respectively given. Okay, so let's do this. Zinc oxide, we have the atomic mass unit of zinc as 65. Since there is only 1 atom, so we need not multiply it with anything. There is only 1 atom of oxide, oxygen, and we have 16 as the atomic mass unit. So 5 plus 6, 11, 1, 6 plus 1, 7, 8. 81 U is the atomic mass unit of your zinc oxide. For the second one, we have sodium oxide. We have 2 molecules of sodium over here. So we will be multiplying 2 into 23 and we will be adding it to 16. Okay. So 2 3s are 6, 2 2s are 4. 46 plus 16. So we will be getting 12, carry over 1, 5, 4 plus 1, 5 and 1, 6. 62U is the atomic mass unit of your sodium oxide. For the third question, for the last question, potassium carbonate. Now this is a complex molecule, but let's simplify it, all right? So we have 2 atoms of potassium over here, okay? So simply we will be multiplying 2 into the given value that we have over here, 39, okay? We have to add, so we'll add. We have 1 atom of carbon, so we'll only add with 12. And we have 3 atoms of oxygen over here, so we will be adding it, multiplying first of all with 3 and then you'll be adding. So 2 9s are 18, 1, 2, 3 are 6.7, then you have 12 and then you have 48. So when you add this 10, 18, 8, 1, 7, 8, 8, 4 and 1, 138. All right, let me check. Yes. So when you add potassium, when you add all the masses together, you will get this as your result, and this will be how you will calculate the molecular mass. Mole concept. The mole symbol MOL is the SI unit of amount of substance. Okay, this is yet another standard by which we consider, calculate, we relate, we compare different quantities of substances. Okay, so mole is the amount of a substance of a system. System could be provided any entity, all right, be it your element, be it your compound, be it your ion, be it your molecule. So anything that contains 6.022140076 into 10 to the power 23 specified elementary entities. An elementary entity may be an atom, molecule, ion, electron, and any other particle or any other specified group of particles. Basically, what we're trying to say here is that any amount of substance, if we were to calculate 1 mole of it, okay, we will be having the number of atoms, or that we will be having 1 mole of, say, any compound, let's say X. So in that compound, be it particle, atom, and whatever it is, we will be having the number of particles that we will be having will be 6.022 into 10 to the power 23. This is a very important special number in chemistry. This number, we call it the Avogadro number, and we designate it with, we represent it with the symbol Na. Okay, so Na, what is Na? Na is the Avogadro constant. The value of Na is this 6.022, basically just a simplified version of this huge, humongous number that you had here, 6.022 into 10 to the power 23. So that is the Avogadro number. And what is mole? Mole is any amount of substance of anything that will have this Avogadro constant as its respective particles. Okay, so when expressed in the unit, mole is written mole to the power -1, and it's called the Avogadro number, this number. Okay, so it's a small cute diagram for you here. 1 mole is 6.02 into 10 to the power 23 atoms, particles, whatever you want to call it. Okay, so this number is fixed, and if you for example, in your numericals, if you want to shorten it for your own convenience, you may, instead of writing this whole chunk every time, you may designate it with only the Avogadro constant, that is Na. Because what is the value of Na? The value of Na is this number itself. Advantages of mole. Now, what is the use? What is the purpose of this mole? The advantage of mole is that mass of 1 mole of a particular substance is also fixed. So basically, the atomic mass of an element gives us the mass of 1 atom of that element in atomic mass units. Okay, to get the mass of 1 mole of atom of that element, that is the molar mass. All right. So to get the molar mass of that element, we have to take the same numerical value but change the units from U to G. So molar mass of atom is also known as gram atomic mass. In simplified terms, what it's trying to say here, is that for example, the atomic mass of hydrogen is 1U. Okay, so if you were to calculate the molar mass of hydrogen, you will only have a look at the atomic mass unit, the unit as in the number. So what is the number over here? The number is 1, and you will replace the unit from U to G. Okay, so for example, the atomic mass of hydrogen is 1U, but when we have to take a look at the molar concept, the gram atomic mass unit is, atomic mass is how you will calculate the molar mass. So the gram atomic mass of hydrogen is 1G. You're only taking the value of that particular element would be the same. So for hydrogen is 1, so the value would be the same. You will only be switching the units from the atomic mass unit U to the gram atomic mass unit, I'm sorry, to the gram atomic mass, that is your G. So just a change and exchange of units. Advantages of mole. Another advantage can be depicted by this picture over here. Suppose this is a tumbler of milk over here, or whatever, water. Okay, sorry. This is a tumbler of water. All right. This is a laboratory size example. So if you were to calculate, to have a look at single molecule of water. Okay, so here is the structure on the left hand side, a single molecule of water. You know, the molecular mass of water would be the sum of the of all the molecular atomic masses of the atoms, that is 18 AMU. Okay, we just learned how to do this in the previous slides. And the Avogadro's number of molecules present in this amount of milk would be how much water molecules would be, how much water atoms? 6.02 into 10 to the power 23. So one mole of water would have this many atoms of water. Also, one molecule of water, since it has 18 AMU, so if you were to calculate one molar mass of water in the level of molecule, okay, so you will be writing the same amount of number that you had in the molecular mass, that is 18, and you will be simply replacing the unit from the atomic mass unit to the gram atomic mass, that is G. So this gram atomic mass works both at the atomic level and the molecular level. So for hydrogen we saw 1U to 1G. For water, since now we are coming at the molecular level, from we are getting from 18U to 18G. Okay. A fun fact is that Mole Day is an unofficial holiday celebrated among chemists, chemistry students and chemistry enthusiasts on October 23 between 6:02 AM and 6:02 PM, making the date 6 to 10 to the 23, that could be 10 to the power 23 in the American style of writing dates. The time and date are derived from the Avogadro number that I just accidentally spelled out, which is approximately 6.02 into 10 to the power 23. So, a fun way, if you want to do it, you can do it too. Mole Day is celebrated, and it is apparently famous among chemists, chemistry students and chemistry enthusiasts. Chemists counting unit. Chemists need the number of atoms and molecules while carrying out reactions, and for this they need to relate the mass in grams to the number. Okay, how is it done? It is done with the help of mole. We know that mole, a certain amount of substance of mole has 6.022 into 10 to the power 23 number, whatever number. So when we have to calculate the mass, we just write the relative mass in grams. Okay, the relative atomic mass at the atomic level or the molecular level or whatever it is. So for example, if you have 16U, oxygen has only one atom of oxygen. One atom of oxygen has 16U. Okay, so we can say that 16 gram of oxygen. Okay, note the difference in the unit. 16U was here earlier that we used to denote for one atom of oxygen, but now here we have taken 16 grams. So we have switched up the units. The quantity is the same, the number is the same, but we have switched up the units, and because we have switched up the units and gram atomic mass is for denoting mole, so 16 gram oxygen has 1 mole of atoms. And what is 1 mole of atoms equivalent to? 1 mole of atoms is equivalent to 6.022 into 10 to the power 23 atoms. So 16 gram has this much atoms of oxygen, and that is how chemists use mole in, making the tasks easier. Illustration 3. Calculate the number of moles for the following. 52 grams of helium. We will be finding mole from mass. So the number of moles, let's designate them with the small letter n. Given mass with the smaller letter m. For molar mass, we'll be taking capital M. For the given number of particles, that is whatever. So for example, in the second example, we have been given some number of particles. So let's designate them by n. The Avogadro number of particles is Na. Okay. What we are supposed to do here, we are supposed to calculate the number of moles. How many moles would be there in 52 gram of helium? Okay. So the atomic mass unit of helium is 4U. The molar mass would be 4 gram. You just have to switch up the units, right? So that means that 1 mole, for 1 mole of helium, the gram would be 4 gram. Or you may also write it in the reverse way, that 4 gram of helium has 1 mole of helium atoms. So okay, so we have 52 grams of helium given over here. We have 52 grams of helium given over here, and we have to calculate the number of moles. So if 4 gram of helium has 1 mole, so how many mole will 52 grams have? It's easy, right? We'll just have to do this, right? That is how it has been illustrated here. So you divide the given mass by the molecular mass, that is 52 by 4, and you get 13. So 52 grams of helium will have 13 moles of atoms. Okay, let's have a look at the second part. 12.044 into 10 to the power 23 number of helium atoms. For this number of helium atoms, you have to calculate the number of moles. So you know that 6.022 into 10 to the power 23, that is the Avogadro number. This is how many atoms you have in 1 mole. So if you were to calculate the number of moles in this given number of helium atoms, you will just simply be dividing, okay, the given number of particles with the Avogadro number, and this is your basic unitary method, and that is how you would be getting 2. So there would be only 2 moles of that. Illustration 4. Calculate the mass of the following. 0.5 mole of nitrogen gas you have to calculate, and the mass is taken from the reference of the mole of the molecule. Okay, so that is, we have to calculate the molar mass in respect to the molecule. Okay, so we have been given the mole and we just have to calculate the mass. So let's first of all calculate the molecular mass of nitrogen. Molecular mass of nitrogen is 28. Okay, so basically one molecule of nitrogen would have 2 atoms of nitrogen. So 14 plus 14, okay, 14 is the atomic mass unit of 1 nitrogen. So 14 plus 14, that would be the atomic mass unit of 1 molecule of nitrogen, and you have to calculate the molar mass. So simply change the units, 28U to 28 grams. Okay, and so 1 mole has this many mass. 1 mole has this many mass. So what would be the mass of 0.5 mole? You will simply multiply it, right? So 28 into 0.5, and then you'll get 14. Okay, so since 1 mole has 28 grams, so for 0.5 mole you will simply multiply 28 into 0.5. In the second sub question, we are taking mass from the respective mole of atom. So instead of taking 2 atoms of nitrogen, we here have only taken 1 atom of nitrogen, that is 14. So simple enough, right? We will just be multiplying 14 into 0.5, because now 1 molar mass would be your 14 gram. Therefore 14 would be multiplied with the number of moles that is given, that is 0.5. For the third sub question, that is, you have to calculate the mass of this many number of 3.011 into 10 to the power 23 number of n atoms. Mass of number. It is very simple. Okay, so the given number of moles n, would be the given number of particles divided by the Avogadro number. This we had already established in the previous example. Okay, so to calculate this, it would be easier for us if we were to calculate the number of moles, and then we would just simply, add, or we will simply multiply the number of gram atomic mass of nitrogen, be it from the atomic level or the molecular level, like we had done in the first two questions. Okay, so we have to calculate first the number of how many moles would be there in this many atoms. So we know that Avogadro constant, this many atoms or particles are there in 1 mole. Okay, so whatever number of particles we are given, if we are to determine that how many moles would be here, we would simply divide this number with the Avogadro number by simply using the unitary method. Okay, so we will divide 3.011 into 10 to the power 23 by this. So the resulted is 0.5. So it's the same thing again over here. We have 0.5 moles, and since we are to calculate mass from number of only nitrogen atoms, so the gram atom mass would only be 14, and we'll be getting 7. In the last question, there is the amount of 1 mole, 6.02 to the power 23 is 1 mole of nitrogen molecules. So we have taken mass from number from the molecular level. Okay, so over here the gram atomic mass unit would be again 28. Why 28? Because we would be taking 2 atoms of nitrogen into consideration. So for this we will apply the same formula that we had earlier. We will be getting the number of moles by N into Na. That is, it's basically the value of 1 mole itself, but for the sake of trying out this formula, it will be simply crossed off 1. Okay, 1, and we will simply multiply it by the gram atomic mass that we already have, 28, and 28 would be the mass, the required mass. Illustration 5. Calculate the number of particles in each of the following 46 gram of sodium atoms. Okay, so first of all, let's calculate how what would be the number of particles in 1 gram of sodium. Sorry, not 1 gram, 1 atom of sodium, by relating the gram atomic unit in relation to that 1 atom of sodium, and from that we can build up that what would be the value of 46 gram. So if you were to do that, okay, so the number of atoms would be given mass by molar mass into Avogadro number. So here that the molar mass of nitrogen would be the molar mass of sodium would be 23 grams. Okay, so we have taken 23 grams, but we have to find the value for 46 gram. Okay, so to find the value of 46 gram, we will be just simply using the unitary method, and we will be dividing 46 by 23 into the Avogadro constant. So what we are doing here is simple. Since 1 mole since 1 mole of sodium has 23 gram atomic mass, and we know that 1 mole has the Avogadro constant number of atoms, right? So this for 1 mole, this Avogadro constant would be there for this one particular sodium atom, but we have to calculate with respect to 46 gram, not with respect to 23 grams. So with respect to 46 gram, we would be calculating by dividing 46 by 23, and then we'll be multiplying this whole result by the Avogadro constant. Similarly, in the second set of question, we have to calculate the same thing for 8 gram of oxygen molecules, number of molecules from mass. Again, for this thing, we know that 16 gram of 16 gram atomic mass of oxygen has 1 mole. Okay, so 16 gram atomic mass of oxygen would have the Avogadro number of atoms present there. All right, so if we were to calculate the number of atoms present for 1 gram, that we would simply be dividing the Avogadro constant by 16, And now if we are to calculate the number of particles present in 8 gram, then we will be simply adding this whole thing with, sorry, multiplying this whole thing with 8. That is what we have done here. 8 into 32. I'm sorry. We are taking oxygen molecule. I'm so sorry. We have taken the oxygen molecule in respect. Fair enough. We will just be adding this whole thing by another 16, since an oxygen molecule is made up of 2 oxygen atoms. So we are getting here 32. So we will simply be dividing 8 by 32 and then newly multiplying it with the Avogadro constant. So the similar thing that I have done here, and that would be the number of particles that are present in 8 gram of oxygen molecules. For the last, and I think this is the easier one, we have to calculate the number of particles present in 0.1 mole of carbon atoms. Now, we know that for 1 mole of any substance, you will have the Avogadro equivalent of particles present in it. So for 0.1 mole, you just simply multiply the Avogadro constant with the 0.1 thing and you will get your desired result. So let's end this chapter with 2 wonderful examples. If 1 mole of carbon atom weighs 12 grams, what is the mass in grams of 1 atom of carbon? Now we know we have taken the molecular mass of carbon atoms as 12 grams, okay? Sorry, the gram atomic equivalent of the molecular mass of carbon, okay? So 12 gram of atoms has 1 mole of particles in it present. So if you were to calculate that what is the mass in grams of 1 atom of carbon, so 1 mole is equivalent to 6.022 into 10 to the power 23 atoms. So this many atoms would have the gram atomic mass of 12 gram in the case of carbon. Alright, and you have to calculate the mass of only 1 carbon. So you will do the unitary method. You will divide this 12 by this number, which is basically your Avogadro constant, and whatever the result would be, that would be your desired value. That would be the desired value for the mass in grams of 1 atom of carbon. Which has more number of atoms, 100 grams of sodium or 100 grams of iron? Given atomic mass of sodium is 23U and for iron is 56U. So fair enough, we go with this question in the similar way that we are doing the previous ones. Alright, so we know that for 1 mole of sodium we have 23 gram atomic mass. Alright, and we have to calculate that how many atoms would be there in 100 grams. Okay, so for 23 grams of sodium, you are having this many number of the Avogadro constant equivalent number of atoms, since for 1 mole we have 23 grams equivalent. Okay, so what would be the value for 100 gram of sodium? Alright, so first we will calculate for 1 gram, that would be your Avogadro constant divided by 23, and then you will calculate for 100 grams. So for 100 grams, you would just be dividing the number of mass that is required divided by the gram atomic mass of sodium, and you will multiply it with the Avogadro constant. In the similar fashion, we will calculate for iron. So we know that 56 gram has 1 mole. 1 mole of iron has the gram atomic mass unit is is 56 gram for 1 mole. Okay, so for 1 gram it will be 1 by 56. Okay, but we have to calculate here not for 1 gram, we have to calculate here for 100 grams. So jumping off to 100 grams, the value would be 100 by 56 into Avogadro constant. Why the Avogadro constant over here? Because 1 mole, any 1 mole of substance has the Avogadro constant equivalent of particles, that is 6.022 into 10 to the power 23. So when you will compare these two values, alright, when you will compare this value 100 by 23 into Na and when you will compare this value 100 by 56 into Na, you will observe that the number of particles would be greater for sodium. The number of particles would be greater for sodium in respect to iron. So when we are taking 100 grams into consideration, so the number of atoms would be higher in 100 grams of sodium with respect to or as compared to 100 grams of iron. We have come to the end of this chapter. Let's have a quick revision. First of all, we looked at the history of atoms. All right. So we looked at the history of atoms. We had different Indian philosophers, Greek philosophers, and different scientists coming in and telling us that atom is the indivisible particle, smallest particle of an element or a compound. But then we had later scientists, that made it possible for atom to be divided into proton, electron, neutrons, so on and so forth. We saw Dalton's postulates in respect to atoms. We saw two important laws that were being explained by Dalton. The law of the conservation of mass was the first law, that in any particular reaction the number of mass would be the same. All right, so mass is neither created nor destroyed. Atoms are neither created nor destroyed. That was the postulate of Dalton. That is how he defended this law. And the second law was of the definite proportion. So two atoms would come together to form a molecule with some definite whole numbers. All right, so that is how Dalton gave the explanation for the two laws. Then we saw how atoms are represented. Atoms are represented by symbols. All right, we saw that atoms are represented by symbols. Then we saw the atomic mass unit, how are atoms measured. Okay, we simply write U for it. Then you saw the IUPAC, that scientific organization, that body that governs that how different elements, how they are named, how they are symbolized, how they function, so on and so forth. And then we had a chance to look at molecules. We know that molecules are a combination of atoms. Okay, and there are some charged molecules as well. Charged because they either have an excess of electrons, or they either have a deficiency of electrons. And all the ions, they are in a constant state of finding the urge to get stabilized. So ions come together in order to attain stability. Cations attract anions and ions attract cations, and we have those are the two sort of ions, charged species. Okay, then from molecules we learned about that molecules can be represented by formulas. We have different formulas to represent molecules, and how can we determine whether a formula is to be written? We can that can be determined by the combining capacity of a specific combining capacity of a specific atom. And how do we do that? We do that by finding out its valency. So valency is basically the excess of electron, or the deficiency of electron that a particular atom or ion is having, and by crisscrossing, by the transfer of that valency, we attain that formula. That is basically the visual representation of the composition of molecules. Okay, then at last we had a chance to look at the molecular mass. We had a chance to look at the concept of mole, how mole is beneficent to the chemists, how when we have the concept of mole, we can also have the concept of gram atomic mass unit. So this simplifies a lot of things, and so this is basically what we learned in this chapter. In the further chapters, we'll be again having another discussion on matter. We'll be having another fruitful session on how matters react, be it on a larger scale or be it on a very minute molecular or an atomic or a microscopic scale. So we'll be having a look at all these. Thank you so much for joining us here today, and we'll be seeing you in the next chapter. Take care and study great.